Hello physics enthusiasts. In this and the next video I will attempt to explain Hawking radiation. And when I say explain, I don't mean the particle pairs at the horizon type of explanation you've heard a million times. An explanation which actually explains nothing. No, what I will do in this and the next video is walk you through the arguments and calculations in the Hawking's paper, the original source. I will make a couple of simplifications just to make things clean, but this will not change the overall picture of Hawking radiation. At the end of these two videos, you will understand why the Hawking effect exists and how it's calculated. No hand-waving, no disappointing analogies. In this first video, we will set up the problem and explain the physics of a collapsing light shell using Penrose diagrams. Hawking considered a collapsing dust because it makes his result a bit more general, but the derivation steps are nearly identical for a light shell. So we are not missing out on anything by preferring this simplified collapsing geometry. Then we will talk briefly about fields in flat versus curved spacetimes and how they are quantized. At the end of this video, you should understand the basic procedure of deriving Hawking radiation with an appetite to see the exact math. In the next video, I will get into the mathematical nitty-gritty of Hawking radiation. At the end of that video, you should have a good understanding of the math and physics behind the Hawking effect. So, with that said, let's go. As usual, I will work in the Planck's units. To discuss Hawking radiation, it is convenient to use Penrose diagrams. If you don't know what a Penrose diagram is, watch my video on the topic. The link is in the description box. In that video, I discussed the Penrose diagram for an external black hole, which looks like this. The coordinates that allowed us to generate this picture are called compactified crystal coordinates. The line labeled past null infinity represents all of space in the far past, while the line labeled future null infinity represents all of space outside the black hole at the distant future. The white line is the horizon at the distant future. This picture only shows the region outside the horizon, which is the only region that is relevant to our purposes. We can also generate a similar picture for flat spacetime in spherical coordinates, which looks like this. A collapsing dust, which is what Hawking considered, that starts out by occupying all of space in the distant past and ends up as a black hole in the distant future, will have a trajectory on the Penrose diagram like this. But we know that at some point the dust will form a horizon. So our diagram stops here. As I said earlier, we will not be considering a collapsing dust, but rather a collapsing light shell, whose trajectory looks like this. Let's look at this diagram in more detail. First of all, we need to make a distinction between the coordinates used to generate the Penrose diagram and the coordinates we'll use for our calculations. Here is the relationship between them. The capital U and V are the coordinates in the interior of the light shell, while the lowercase u and v occupy the outside of the light shell. Note that the times in the two regions are not the same. In the interior of the null shell, where the metric is Minkowski, we have tau that labels the passage of time, which is very different from t, which keeps track of the time outside of the null shell, where the metric is Schwarzschild. Initially, when the null shell is infinite, these two time variables are the same, but as the shell approaches the horizon, tau approaches a finite value, while t approaches infinity. In the xt coordinates, the lines intersect at these values. There is another line representing what's known as the last photon that will be important later, so let's draw it too. From now on, we will not be using x and t axes, but rather the u and v axes, which run at 45 degrees to t and x. The range of these variables is this. What we want to do is to keep this picture, but use the calculation variables. So let's replace the ranges of the diagram variables with those of the calculation variables. And let's also change the color of this segment. Okay, now that we have a detailed Penrose diagram for both the flat and the collapsing spacetime, we need to talk about fields that live on them. In particular, we want to study the behavior of a real massless scalar field phi, whose Lagrangian is this. The equation of motion is given by the Klein-Gordon equation. In the coordinates t, r, theta, phi, this equation is second order in time, in both the flat and the Schwarzschild spacetime. That means that, in order to obtain a unique solution, we need to know the initial phi and phi dot everywhere in space. In a four-dimensional spacetime, this is equivalent to saying that we need to know initial data on a space-like slice, called Cauchy surface. Our goal is to find a field that is not only a solution to the Klein-Gordon equation, but that is also quantized. That is to say, the field can be written in terms of some basis f and coefficients a, such that the commutation relation between phi and its canonical momentum pi satisfies. The notion of a particle is then defined by the operator a. Another, more conventionally accepted way to say this is that a defines a positive frequency mode on a Cauchy surface. Since the coefficient operators do not depend on a spacetime position, quantizing the field in an arbitrary slice, or Cauchy surface, will determine the field on all such surfaces, or in other words, for all time. We can do the same thing for the stationary Schwarzschild spacetime, since t is a Killing vector for both cases. A Killing vector is simply a direction in spacetime along which the metric doesn't change. However, in a collapsing geometry, no global time-like Killing vector exists, so different observers cannot agree on what a vacuum is. If one observer defines a positive frequency mode, it will appear as a mixture of positive and negative frequency modes to another observer. In more mathematical terms, quantization of fields on different Cauchy surfaces will yield different operator coefficients and hence different definition of positive frequency modes. To use a collapsing geometry as an example, the Cauchy surface in the distant past would look like this. However, in the distant future, once the black hole has formed, it will look like this. Now there is a hole in the surface. More precisely, the surface has split into the space outside the horizon and the horizon itself. So quantizing the field on the first surface will yield a coefficient operator a, while quantizing on the second surface will yield a different operator, say b, for the space-like surface and c for the horizon. That means that if the observers at distant past measure zero particle content on their Cauchy surface, in other words vacuum, the observers in the distant future will measure a non-zero particle content. Okay, let's go back to our Penrose diagrams. We can define Cauchy surfaces for the variables u and v. For example, the past null infinity is one, the future null infinity is another. We could show that on this diagram, defining a positive frequency for each of the Cauchy surfaces will lead to the same vacuum. We simply write the field on one surface in terms of f and a, then write the field on the other surface in terms of p and b. Since having Cauchy data on one surface determines the field on the entire diagram, we can write the field in terms of the b operators on the past null infinity. Since both f and p are basis functions, we can write one in terms of the other. I suppress the u equals to minus infinity part. Equivalently, we can write the b operator in terms of the a and a dagger like this. These are called Bogolyubov transformations. Thus, the observer at future null infinity would measure the expected number of particles given by this. However, if we went ahead and computed f and p, we would discover that they are in fact the same. Thus, in flat spacetime, the matrices alpha and beta are Kronecker delta and 0 respectively. The observers at future null infinity would observe the same vacuum as observers at past null infinity, as would observers at any other point on the diagram. Another way to put this, in flat spacetime, positive frequency remains positive frequency forever. The situation is quite different for the collapsing null shell diagram. Following the quantization procedure we just discussed, we can define the field phi on the past null infinity. Now let's define the same field on the future null infinity plus the horizon. Recall that defining a field on a Cauchy surface fixes the field uniquely everywhere on the diagram. So, now that we have two ways of writing the same field, we can figure out how they're related. To do that, we can use the same technique as Hawking did in his paper, the so-called ray tracing method. We know that on the Penrose diagram, all propagation of massless fields will be along the u and v directions. So, if we pick a point on the path null infinity, we can trace the v mode, that is, the mode that does not change along the v direction, to the center. The mode then reflects off the center and propagates to the future null infinity. A quick side note. What do I mean by the mode reflecting off the center? When a spherical wave propagates towards the center, its radius shrinks. Then, when the radius becomes 0, the wave starts propagating outwards, such that its radius increases. And that's all really. It looks like the wave bounces off the center. We can do this for all points on the pink line, up to the last photon. Past the last photon, the V modes will propagate to the horizon and fall into the black hole. So now we see that in order to have a one-to-one correspondence between the past and the future, we need to include the horizon if we want to have a complete set of modes. Now, as we did before, we can relate the p basis to the f basis. V sub h here denotes the value of V for the last photon. Recall that its value is 0. In Hawking's paper and many other sources, people don't bother assigning values, to keep things general, I guess, but here we will set it to 0. So explicitly, the relationship between phi minus and phi plus is... Again, I have suppressed the u equals to minus infinity bit. Now we just repeat what we've done before. Expand p in terms of f, which leads to this relation between the b and a operators, and of course to the particle expectation number. Now, however, the beta matrix is not 0, because the p and f functions are very different. So the observers in the future null infinity will see particles. The collapsing geometry changes the future vacuum state. We started in a state with 0 particles in the infinite past, when the spacetime was flat. Then, a light shell collapsed into a black hole, leaving a Schwarzschild spacetime in its wake. And even though observers far away from the black hole have experienced flat spacetime the entire time, their vacuum state has changed, which is rather remarkable. We can also ask what is the relation between the A and C operators. But since this part does not contribute to Hawking radiation, we will leave it for a future video. So, there isn't much else to say in this video. Hopefully I have been clear enough to convey the structure of the problem and the reasons why Hawking radiation is inevitable in the collapsing geometry. In the next video we will fill in all the mathematical details and compute the celebrated Hawking temperature. Until then, I wish you a nice problem-solving day, and cheers!